Well, thank you very much, and I want to thank you organizers for organizing what's been it's been a fun conference. It's been great talks. Obviously, the talks are okay, but the view is even better, right? It's been a really just fun time. So I'm going to talk about the second homology for the Torelli group. So I'm going to, I give a very, very, very specific title, right? But I'm going to try to give a very broad talk because this is a fairly broad audience. There's a lot of people. It's homotopy theory. There's people working in dynamics. There's people working in representation theory. So I'm going to spend the vast majority of my talk giving background, giving explanations for what the things I care about are and why you should care about them. And then I'll get to my own theorems maybe in the last 3 to 4 slides. Okay, so this is a talk about low-dimensional topology. So oftentimes, when you think low-dimensional topology, you probably think like, 3 manifolds, 4 manifolds, knot theory. But I really mean something much lower dimensional than that. So let sigma G be a compact-oriented genus T surface. And there's a genus 3 surface right there. So, I remember when I was a student, right? I learned the classification of surfaces maybe when I was like 19 or something. And thought, yeah, I'm done with 2 manifolds. Let's get on to the more interesting things. But and somehow the fact that we know the classification of surfaces, which and we've known that since the 19th century. This is actually an amazing theory. If you think about it, it was proven by Möbius for the first time, sort of state that we would recognize today. And that predates the definition of the topological space for a manifold. So this is, this is how you can tell a real great theorem, right? If every time the foundations change, the theorem stays the same, right? That's anyway. So this is so once you know the classification, you can start asking more sophisticated questions. And so what I want to talk about is what's called the mapping class group. So the mapping class group, which I'm going to denote by mod G, is the group of homotopic classes of orientation preserving homeomorphisms in the surface. There's a lot of, the precise adjectives here are less important. You could replace homeomorphisms by diffeomorphisms. You could replace homotopy by isotopy. All these things. And in dimension 2, there's really no difference in any of these categories. And so, it's just self-maps to the surface in whatever category you want, up to whatever kind of deformation you want. So this is an extraordinarily rich group. It's somehow everywhere dense in mathematics. Everyone has things they can say about it. And so what I want to talk about today are cohomology and finiteness properties of the mapping class group and its subgroups. I'm going to focus less, there's sort of two things you can do here. So you could focus on specific cohomological computations, and that's a very interesting subject and a very rich one. But I'm going to focus less on specific cohomological computations than on sort of more coarse questions like, is the cohomology finitely generated? Is it finite dimensional? What kinds of things can you say about that? What happens when we pass to subgroups? Okay, so that's the theme of this talk. So before, so this is a group. Before you can start thinking about sophisticated questions like what is its cohomology, you should have a sense of maybe some elements of the group, right? You should be able to write down some things. And so, here's the first thing you might think about when you're trying to write down some self-map of a surface. Let R from sigma 4 to sigma 4 be the rotation by 2 pi over 4 that I've written right here. I've drawn it in such a way you can see where that little loop gamma goes. Gamma goes to R gamma. It's 1/4 click around. I guess that would be counterclockwise. Okay, so that's a self-map of the surface. But of course, it gives you an element of the mapping class group. But why does it give you a non-trivial element of the mapping class group? And that's a little puzzle for you. And the answer, of course, is staring at you right in the face right there. The answer is that, gamma right there, there's R gamma, there's gamma. Those are 2 different elements of the first homology group of this genus 4 surface right there. So this R is not homotopic to identity. It defines a non-trivial element of the mapping class group because it acts non-trivially in the first homology group of the surface. Now, there's actually, R is a finite order diffeomorphism or homeomorphism of the surface, and this technique for seeing that as a non-trivial mapping class is actually the universal one. So there's an amazing theorem. It's combines work of Hurwitz from 1892 and Nielsen from 1943, and it says for all G at least 2, if you have a finite order diffeomorphism of the surface, it's going to act non-trivial in homology and thus give you a non-trivial element of the mapping class group. So any finite order self-map of the surface is going to be a non-trivial mapping class for the dumbest possible reason because it acts non-trivial in homology. Of course,
isn't true in genus 1, right? So if you have a torus, you can do like a little rotation of the torus a little bit. That's homotopically identity, right? So this is really thinking about higher genus surfaces. So this paper of Hurwitz from 1892 is a really interesting paper. This is the paper that reproves the Riemann-Hurwitz formula. And it's well worth reading today. I mean, it's in German, but it's not that bad. It's not that long, and it's recognizable. You know what he's doing. You can read it from today's viewpoint. So what Hurwitz actually proves, well, he proves this thing about the finite order elements of diffeomorphism. I guess I actually stated this incorrectly. I said this requires Nielsen. So the way I stated this actually is the theorem of Hurwitz. What Nielsen showed was something else. I should have said finite order elements of the mapping class group at non-triviality. So there's a difference between, there's a sort of a priori difference between a finite order element of the diffeomorphism group and a finite order element of the mapping class group, right? If you have a finite order element of the mapping class group, that's some self-map F, such that some power of it's homotopically identical. And that's what Nielsen proved, is that in fact there is no difference. If you have a self-map of the surface such that some power is homotopically identical, then in fact you can homotopic so that some power is literally the identity. Okay, so for finite order elements, everything works in the simplest possible way you can imagine. Okay, so those are finite order elements. Another basic element of the mapping class group that's worth knowing about are what are called Dane twists. These are this would be the next simple thing to write down. So let X be a simple closed curve, a loop on our surface. And the Dane twist T of X, what do? When you have a loop on your surface, you cut it open along the surface, pull it apart, give it a full 360-degree or 2 pi twist and re-loop. And so you can sort of visualize what it's doing based upon what it does to an arc that traverses, that's transverse to that loop X. You can see when you cut along X, twist and re-glue, the arc picks up a copy of X. It kind of goes around X and then keeps on going along its merry way. Okay, so that's a Dane twist. They were discovered by Dane, of course. And Dane in 1938 proved that the mapping class group was generated by finite many Dane twists. And then Stephen Humphreys discovered this specific set of elements, 2G plus 1 Dane twist, the loops I drew right here. Those Dane twists will actually generate the mapping class group. This theorem of Dane, by the way, it's like a little fun piece of history. So sometimes these are, it was sort of forgotten because low dimension topology was in its infancy. And so it was rediscovered, I think, in the 60s by Raymond Licorice. And so briefly, these were called licorice twists, you know, but unfortunately, you know, sadly, we can't keep that one up. But anyway, but here's a puzzle. So when you first see this, you think, yeah, okay. So I can get a mapping class. I just start taking some Dane twists and composing them. But it's not straightforward to sort of see how an element of the mapping class group can be written as a product of Dane twist. So here's a fun puzzle, which I'm not going to solve for you. That rotation I wrote in the previous slide, write it as a product of, forget these Dane twists. Write it as just a product of any Dane twist whatsoever. And it's not so easy to do. I think any expression for it's going to involve like 20 or 30 different Dane twists. It's going to be some gigantic word on the page. And if you stared at it, if someone handed you that word, you would have no way of recognizing that it was a finite word. So just knowing the fact that it's generated by Dane twist, that's a nice thing, but it's somehow, you should think of it as telling you what the typical element of the mapping class group is. In the same way that, you know that, say, matrices are products of elementary matrices if they have determinant 1, right? So elements of SL2 are products of elementary matrices, but a typical matrix is not an elementary matrix. A typical matrix, the eigenvalues are all over the place, it's a giant mess, right? And so similarly, that you should think of a typical element of the mapping class group, not as something to find order or as a Dane twist, but as something that really mixes the surface up. It takes every point and sort of goes all over the place right there, and you can't really, you don't understand it by writing it as a product of Dane twist. But there is one thing here that's somehow a more conceptual property rather than computational property. It says the mapping class group is finitely generated. That's not an obvious fact at all. It should be a little, it should be a little surprising. This is false. And by the way, this is false in higher dimensions. In dimensions, I think at least 5, the mapping class group of tori are not finitely generated. They contain F2 to the infinity. They're non-trivial extensions of GL and Z by F2 to the infinity. So it's very, so you should, this is somehow the fact that the mapping class groups tend to be finitely generated is a special feature of low dimensions. Okay, so those are some elements of the mapping class group. So the next thing I want to talk about is
Well, why should you care about the mapping class group? Why is it something that is of interest to a broad swath of mathematicians? And so there's a lot of answers I could give to that. There's more obvious answers, say in low-dimensional topology, if you want to move three manifolds together from pieces, for instance, the mapping class group is going to tell you what the gluing data will be. But I want to give an answer that will feed into the next thing I want to talk about. And so the answer I want to give is that the mapping class group is absolutely fundamental to the study of what is called monodrome. So what is monodrome? So I'm going to begin with the lowest dimensional example involving surfaces, at least. So let M3 be a three manifold and phi from M3 to S1 be a fiber bundle over S1. Okay, so we have a three manifold that fibers over the circle. It kind of looks like that, right? So we have a circle's worth of surfaces. But this is sort of the deceptive picture because this looks like a product of a surface across a circle, right? What's really happening is that if you go around that circle, the surface twists around. And so as it twists as it goes around S1, what's really happening? So you start here at some base point, some base fiber. You look up as you wander around the surface is moving around, things are happening. You come back and you're at where you started. The surface has changed, right? The surface is not where it was. And the sort of difference between where you started and where you ended is given by some map F of the surface to itself. And that's another way of saying that would be that the three manifold M3 is the product of sigma g cross the interval 0, 1 modulo the equivalence relation, but the equivalence relation lose sigma g cross 0 to sigma g cross 1 via some diffeomorphism F. And of course, there's various choices we've made. And so in reality, it's just, it's what really matters is the homotopy class of F. And so that's the thing that's the thing that sort of records what's going on here. That F is called the monodromy of this three manifold that fibers over the circle. So it's there are many so the monodromy, if you fix how is it associated to this three manifold? Well, you have it's associated with the three manifold, the fibration or the fiber bundle over S1, plus a choice of an identification of the fiber over one point. It's like some base point. But once you've done that, and this gives you for every such three manifold with that data, an element of the mapping class group that records how it twists as you wander around the surface. So this is a simple example of monodromy. What happens in higher dimensions? Well, in higher dimensions, we generalize that. We generalize the circle to some higher dimensional base b to the n. The b to the n is supposed to suggest that it's a high dimensional manifold, but of course it can be anything. And it looks sort of like this, right? So we have the base b, which I've drawn. I'm not very good at drawing complicated three-dimensional pictures, and so this is just a flat plane right here. And above every point of the plane, we have a surface. Okay, so we have a b's worth of surfaces, right? Above every point of b, we look up when we see a surface. So how can we understand that information? Well, let's think about a circle inside b, right there. So there's a circle in the space, and if we take the pre-image, well, the pre-image of that circle in this fiber bundle is going to be actually a three manifold, right? Because it's a fiber bundle. It's it's not a trivial fiber bundle over that circle, but it is, it's some three manifold lying over that circle, and it's got some monodromy, right? That because it's a three manifold. So above every circle, we have a three manifold fibering over S1, and associated with such a thing is a monodromy. So there's of course, the sort of natural thing you think of circles in B and the way I drew this, the circle's embedded. And when I say it, literally the pre-image is a three manifold, that means the circle's embedded. But of course, you can just, instead of looking at the pre-image, you should take a map from the circle to B and pull back the fiber one, and then you get a three manifold. That's the sort of more precise way of saying this. So for every circle mapping into B, we get an element of the mapping class group. And these assemble together to give you what's called the monodromy representation of this fiber bundle. This is a representation from the fundamental group of the base to the mapping class group. There's, of course, you choose the base point of B, you choose an identification of the base fiber, that pins down exactly what the monodromy representation is. Okay, and pi 1 of B depends on homotopy classes of circles. That's why we're modding out by homotopy in the mapping class group anyway. So all those choices don't matter. Okay, so we've associated have fiber bundles over a space with fiber surface, we've associated a representation of the fundamental group of the space into the mapping class group. That's an interesting invariant of this. And in fact, it's a complete invariant. As long as B is a reasonable space. There's a theorem of Earl and Eels from 1969 that says that in fact, a surface bundle over base B is determined by its monotony representation. Maybe you need the surface to have genus at least 2 for this to be true. Okay, but when I say surface, I mean a surface of genus at least 2. Okay, so what did Earl and Eels actually prove? What they actually proved was that the surface of genus at least 2, the identity component of its diffeomorphism group is contractible. Okay, and they proved that basically, they proved that using complex analysis, using different, sort of techniques coming from geometric analysis, in particular the theory of quasi-conformal maps. Okay, which is a long other story that I could be telling right now. That's somehow surfaces are so low dimensional that every part of map has something to say about them, like because you can put them in anything, and in particular, like the theory of conformal and quasi-conformal maps plays a fundamental role, not just in like the geometry of surfaces, but even in the topology, even in the study of things like the mapping class group. And so this is a purely topological statement, but really, I guess there does now exist purely topological proofs of this, but they're not that elegant. The proof of Earls and Eels is really, it studies the space of conformal structures of the surface and things like these and so it's quite a beautiful. Anyway, so the mapping class group completely encodes these monogermy representations. Okay, so that brings me to the next topic I want to talk about. This is the reason that I care about the mapping class group. This is sort of my internal motivation, and this is the moduli space of curves. And so here's a definition. An algebraic curve, in this case, algebraic curve for me means smooth and over the complex numbers. It's the vanishing locus of a collection of polynomials in projective space, which happens to be diffeomorphic to a genus G surface. Okay, that's what a smooth complex algebraic is. Now, there are many such things. You're choosing a bunch of polynomials that vanish, and looking at their vanishing loci, you could, for instance, vary the coefficients of those polynomials, right? So these things, they're not topological objects. They're geometric objects. They can be deformed. They come, they appear. They live in families. You can deform them, and the space MD, the moduli space of genus G curves, is a space parameterizing all the ways to deform these genus G algebraic curves. So it's a space. I'm not telling you what the topology of the space is, but the points of the space are isomorphism classes of genus G algebraic curves. So this was first dreamed about by Riemann in the 19th century, who couldn't define it and couldn't compute its dimension. Strangely enough, like he had no idea what he couldn't define it as a topological space, but he knew what dimensional space it was. The answer is 6G minus 6, or 3G minus 3, depending on whether you are thinking of real dimensions or complex dimensions. And then a substantial part of the history of 20th century algebraic and complex geometry was the quest to construct the space from various points of view. And so that construction was finally achieved sort of from the point of view of Riemann in the 1950s by Walter Bailey using data functions. But then the algebraic geometers want to work not just over the complex numbers, but over things like the integers. And that was achieved in the 1970s by Deligne and Mumford. So, since this is the conference on higher structures, right? That the theory of stacks was developed precisely so Deligne and Mumford could construct this space. I'll say more about that in a second. Okay, so this is a space. When someone tells the definition, you can imagine moving around in it. You just, deform coefficients of polynomials, but it's very hard to recognize when two algebraic curves are the same thing. So you should say, like, you should feel inadequate to visualize what the space is. Is it, what kind of thing is it? Well, one theory about it is that it's a 3G minus 3-dimensional quasi-projective, right? That's the complex dimension. So it's 6G minus 6 real dimensions. It's a quasi-projective variety. It has some singularities. It's not smooth,
Sorry, is this a higher structure?
This is I said a stack. It's a stack. Yeah. I said it's a variety. But what I really mean is a stack. A stack is a two-categorical object. I think that counts as a higher structure.
Data.
Yeah, that's right. Well, I've only given you two. I've done some topology, I've done some higher structures, but I have not yet done any representations. That'll come later. So, not any representations, but no, those are linear. I'm going to give you an honest to goodness linear representation.
That's still thinking.
Yeah, okay. So I've already won. I can sit down now, right? So, okay, this is a 3D minus three-dimensional fuzzy curvature variety. So how do we, what's the first thing you could do to try to study its topology and get a handle on it? Well, lying over MG is what's called the universal curve. The universal family, right, is MG1. What is it? It's the space of pairs B comma P, where B is a point in MG, so an algebraic genus G algebraic curve, and P is a point in B. So we just have, above every point, we sort of take MG and we put above B, we put a copy of B, right? Okay, so that's got a projection from MG1 to MG. You just forget that second point is P, and that is a fiber bundle, fiber of the surface sigma G. And it has a monodromy representation, right? I just talked about monodromy representations. We have a fiber bundle whose fiber is a surface sigma G, so we have a representation from its fundamental group, the pi1 of MG into the mapping class group. And there's a theorem of Prof and Klein from 1897 that says, in fact, this is an isomorphism. So the fundamental group of MG is in fact the mapping class group. And so this is why algebraic geometers care deeply about the mapping class group. Now, this statement is not literally true. So, and unfortunately, this is, but it's true in a sense that it's appropriate for this conference. So, so I said this is a moduli space, and so moduli spaces, one lesson you learn as you try to construct them, you try to construct spaces parameterized in geometric objects, is that if you have objects that can have symmetries, then it becomes very subtle to construct their moduli spaces. You have, in particular, if you want their moduli spaces to satisfy some sort of universal property, you want them to not just have the points parameterize isomorphism classes of objects, but you want this map into the space to represent families of your objects, families in this case of algebraic curves. And if you stay in the land of spaces, then it's impossible. These such universal curve properties just do not hold. There's no way to construct them. But in the two categorical land of stacks, that problem is solved, so I'm not going to tell you what a stack is, it's not so important. But one thing that it records is, you have a space of points and each point might have some sort of finite symmetry group in this case. Okay, so you have to reinterpret, when I say quasi-projective variety, I really mean quasi-projective stack. In the land of stacks, it's actually smooth. There's no issue with singularities because the sort of singularities are sort of reflecting curves with automorphisms. And so if you record those automorphisms, the singularities disappear. And then it has a fundamental group in the category of stacks, and that fundamental group is the mapping class group. And you might complain that Prof and Klein in 1897 did not know what a stack was. But in the same way, yes?
So does this mean that every element of the mapping class can be represented by an isomorphism of algebraic curves?
No, it doesn't mean that, because if you have an algebraic curve of genus at least 2, then its automorphism group is finite. And so the mapping class group, so there's a universal cover of MG, it's called Teichmuller space. And the mapping class group acts on it with finite point stabilizers. So if the mapping class group were the automorphism group, if everything in the mapping class group was an automorphism with some algebraic curve, that would be a pretty wild action, right? Every point would fix lots of, there'd be the quotient would be really a sort of much more terrible object than what I'm talking about right here. So Prof and Klein sort of knew this theorem. They had what I recognize as a rigorous proof, even though they didn't have the language to express it, but they did in fact prove something that is equivalent to this, and that today you would recognize as a proof of this theorem. They defined MG in a different way. They defined it as a representation variety, but in any case, you do have to. Oh, the live stream is comparing. I'm not sure what's going on. So in that case, so this is why algebraic geometers care about the mapping class group so much, because the moduli, algebraic curves are the most basic objects in algebraic geometry, and this is the fundamental group of their moduli space. But in fact, something even better is true. So this is a theorem that was discovered by Teichmuller in 1939, that in fact, in the world of stacks, the mapping class group is an Eilenberg space in the mapping class. So its universal cover in the category of stacks is actually contractible. And that's this Teichmuller space I talked about in the previous thing. And so in particular, the homology of the mapping class group is the same as the homology of the moduli space of curves. I wrote this with integer coefficients, and that's if you interpret things in terms of stacks, this is true with integer coefficients. If you just think about, if you don't know about stacks, you just think about this as a naive, sort of slightly singular space, then this is homology statement is true at least with rational coefficients. Okay, so this is a, now you notice that I did not capitalize Teichmuller's name, and that was intentional. So Teichmuller was in fact an avowed Nazi. He died fighting on the Eastern Front. And so I got this idea from Barry Simon. So there's a lot of mathematicians that are genuinely great mathematicians whose ideas we should celebrate, but whose lives we should not celebrate. In particular, there are many Nazis among great mathematicians, not just Teichmuller. And so he suggested that we should attribute theorems to them by their name, but we should stop capitalizing their name to give a subtle suggestion to the reader that we're not honoring them as a person. So I've taken that, I've adopted that practice. So Teichmuller proved this theorem right here, that it's not, and so therefore, if we want to study the cohomology of the mapping class group, we should study the cohomology of MG. Okay, so now I think the main theme of this conference, meet my conference, it's the main theme of this conference, right? Are finiteness properties of these spaces right here. And so the MG is a quasi-projective variety of complex dimension 3G minus 3. So that tells you some finiteness properties of the cohomology of the mapping class group. It says, for instance, that its cohomology, at least rationally, because I'm ignoring the stacking issues, vanishes in degrees greater than 6G minus 6. But unfortunately, MG is not a compact variety. And you already know that it can't possibly be compact, because you can imagine if you have an algebraic curve, it's defined by some polynomials, you could vary the coefficients of the polynomials. If you start doing that a little bit, it'll stay smooth. But if you vary the coefficients too much, you will degenerate your algebraic curve to something singular. Okay, and so degenerating a curve to something singular, that's the same thing as having a path that starts in MG and leaves MG, because MG is just parameterizing smooth curves, right? And so this is not a compact variety. And so therefore, a priori, this doesn't tell you anything about the finiteness properties of individual homology groups. However, in fact, this does imply that it implies two things. It implies the mapping class group is fundamentally presentable. So it's given not just by finitely generators, but also finitely relations. And also each homology group of the mapping class group is finitely generated. So I want to give you this argument right here. So this is really a thing about the homology of quasi-projective varieties. But it's not like a strange or like sophisticated thing about them. It's actually quite simple. So here's the proof. It's a 4-line. And because you should give a proof here. So this is my 4-line. Okay, so MG is a quasi-projective variety. What does that mean? What it means to be a quasi-projective variety is that it's an open subset of its closure in some projective space, right? So we can take MG, we can compactify it to get a projective variety. Okay. What we're doing there? I mean, there are actually many explicit compactifications of MG that are known. One sort of idea about what you might do to do this is, I told you, these paths that leave MG, they start in MG and then vanish off the edge. They really correspond to degenerating curves. So you could compactify it, say, by allowing certain kinds of singularities of your curves. You have to be a little careful. If you allow any singular curve whatsoever, you're going to get something that's not Hausdorff. I mean, you're going to run into trouble. So, but if you're careful, you can add just enough singularities to make this thing a projective variety, so compact Hausdorff and so on. Okay, so we can compactify it, but why is that implied as these finiteness properties? Well, so MG bar, that's our compactification, and the boundary that we attach, the boundary of MG, that's MG bar minus MG, those are both projective varieties. Remember what it means when I say compactify, MG is an open subset of MG bar on well, either the Zariski topology or the classical topology. And so therefore, both mg bar and the boundary of mg bar minus mg are both closed objects in projective space. Okay, so they're both projective varieties. Projective varieties are compact. And they're not just compact. So it's a familiar fact, and one that I think everyone here would agree with, that if you have a compact manifold, then its fundamental group is finite presented, its homology groups are finite dimensional. And the reason is because you can probably if it's smooth, you can triangulate it, as a finite simplicial complex. And the same thing is true for variety. If you have a compact variety, a projective variety, you can triangulate it as a finite simplicial complex. Okay? And here we have mg bar, and we also have this boundary of mg, that's a subspace, and we can there's a sort of relative version of triangulation here. The same, if you have a manifold and you have a properly embedded submanifold, everything's compact. You can compactify the manifold such that the submanifold is a subcomplex. Same thing works here. You can triangulate mg bar such that the boundary of infinity is a subcomplex. Okay, and what does that mean? That means we have written mg as mg bar minus the boundary of mg. This is a finite simplicial complex minus some other finite simplicial subcomplex. Right? That clearly has finitely generated homology groups. If you take any finite simplicial complex, you delete a subcomplex from it, it's no longer a simplicial complex, right? Because if you have, say, like an edge, and you delete the endpoint of that edge, like the open interior of the edge is still there, right? You deleted just the endpoint. Same thing, you have a triangle, you delete one side of the triangle, but not the other two, So but it definitely has the homotopy type of a finite simplicial complex. Yes?
Shouldn't K1G1 be three-dimensional because 1G contains elements of higher order?
Yeah, I'm working in the category of stacks. Yeah, so there's other ways of getting around that, more classical ones. You could pass to a finite index subgroup of the mapping class group that's version-free, that passes to a finite cover of MG that is no longer a stack, but an honest to goodness space. So. In any case, but this, I've been told many times that, the mapping class group is finitely presentable because MG is a quasi-projective variety. When I first heard that, I thought, oh, that's some sophisticated theorem about finiteness properties of varieties, but it's really a non-sophisticated theorem. It's the same reason that, if you have a compact, manifold, and, it's going to have finite generated homologies. It's like one step away from that statement right here. Okay, and by the way, so the fact that the mapping class group is finally presentable that's going to be attributed to Hacker and Thurston in the early 80s. But all the facts I used here were known by the 1950s. So it's one of these funny things, like different groups of people mathematics are not talking to each other. So they didn't realize, that people that cared about topology thought that whether the mapping class group was finally presentable was a hard, open question that they put a lot of effort into, and people like Hacker and Thurston, two of my heroes, put a lot of effort in improving this, but in fact it was already known. They had just talked to the right people and realized that. Anyway, so that's a lesson to us all, right? Anyway, so that is finiteness properties of the mapping class group. So now I want to move into the second topic of this talk, the other thing on the title, which is the Torelli group. So what is the Torelli group? Well, the mapping class group of the surface, these are diffeomorphisms of the surface up to homology. Right? And so that acts on the first homology of the surface, and that's how homology works. It's a homotopy functor. And so that's an action. So H1 sigma G is Z to the 2G. So we get some action on Z to the 2G, but it preserves a form, it preserves the algebraic intersection pairing, given by form graduality. And so that's a symplectic form. And so therefore, this gives us a representation from the mapping class group into SP2Gs. Okay, just given, given a mapping class, you look at the matrix representing its action on the first homology of the surface. Okay. Then that classically, that was proven in the 19th century that this map is surjective, in a different language, of course. Okay, so the kernel of this representation is the Torelli group. So we're going to denote that by IG. The word Torelli group, actually, that comes from Torelli's theorem, which is a theorem in algebraic geometry. The algebraic geometers cared about this before the topologists cared about it. It was named, actually, I believe, so what was really named was its classifying space, which was called Torelli space, which was named by Prof. So, and we denote that by IG for reasons I don't want to go into. And it's the subgroup of the mapping class group consisting of mapping classes that are trivially on the first homology of the surface. Okay, so it's a subgroup of the mapping class group. It fits into an exact sequence like this. One goes to Torelli, goes to the mapping class group, goes to the symbolic group. And so what do I want to talk about? I want, for the rest of the talk, I want to talk about finiteness properties of this Torelli group. Okay, so I just, explained to you why the mapping class group has essentially every possible finiteness property you might want. But how about the Torelli group? What can you say about its topology and its finiteness properties? Okay, so before I do that, though, I should tell you, we have I told you, when you have a group, you should go to write down some elements of it just to get a sense of what kinds of things lie inside there. So let me tell you some elements inside the Torelli group. So the preparing live stream, I wish I could make that go away, but unfortunately, I don't think I have that power. Hopefully that won't block anything. So the Torelli group is I just wrote down its definition there since I just told it to you. So yeah, no one knows. No one knows anything. I mean, I think that's a lesson of mathematics, right? So I just wrote that definition just so you can remember. Okay. So now remember, inside the mapping class group, we have these Dane twists, right? We have a simple closed curve X. T sub X is the Dane twist. We cut along X. We have a full 360-degree twist and redo, right? And if you think about it, how would a Dane twist act in the first homology group? Well, I drew this picture before. Maybe I should have put this picture back on the slide. So the picture of the way a Dane twist acts, it's sort of, you can visibly see what's going on in homology in that picture that I drew, which I will redraw right here. So let's see here. So we have here's our surface. Here is the curve X. And if we Dane twist about X, well, what happens? Well, it's kind of hard. It just surface goes back to itself. So I've drawn a complete picture, but maybe not the most enlightening picture. If you think about what a transverse curve does, what it does is every time it hits X, it goes around the surface, around X, and keeps on going. And so you see, when you action the Dane twist of homology, you represent a homology caused by a cycle of the surface, a bunch of loops. Every time that cycle intersects X, you add a copy of X to it. And maybe you a sign plus or minus 1 depending upon the sign of the intersection. Okay, so the action on homology, this is a formula, it's called a symplectic transvection, but really the important thing for what I'm about to say is that the action of the Dane twist on homology is determined by the homology class of the curve you're twisting about. You're adding a bunch of copies of that homology class to any other homology class depending on the signs of some intersections. Okay, so the action of the Dane twist is determined by the homology class of the curve you're twisting about. And so that gives us a way to write down some elements of the Torelli group. So for instance, if X is a null homologous curve, a curve that's 0 in homology, then the Dane twist about it is going to be a Torelli. So we call these separating twists because remember a curve X is null homologous, that means a boundless subsurface. Simple closed curve. So here's an example of one of those things right there. And I'm sorry, I've tried, when I teach calculus, sometimes, people's phones go off and there's some kind of song and I've taken to awkwardly sort of dancing in front of the room until they find it in the pocket and shut it off because then they're so humiliated, they don't let it happen again. Anyway, so this X right here, the Dane twist about, you can sort of visibly see every time a curve crosses it, you add X to it, but that's adding 0. So this is an element of the Torelli group. Another thing you can do, let's say you have two curves X and Y such that with some orientations they are the same homology class. Okay, and they're disjoint. So here's an example, X and Y, these are two different, these are non-zero homology classes because they're non-separated curves, but they're the same homology class because they co-bound a subsurface, right? So their union is a bounding with appropriate orientations. And so therefore Tx and Ty do the same thing to homology, right? And so therefore if I do Tx, Ty inverse, I've done something to homology, then I've undone it, right? And so therefore, Tx, Ty inverse lies inside the Torelli group. So this is what's called a bounding pair map. You can see it's bounding, it's a pair of disjoint curves that bounds. And so that's why it's a bounding pair map. And it's a theorem that was combines work with John Berman from 1971 with work of her student Jerry Powell from 1978. That the Torelli group is in fact generated by separating twists and bounding pair maps. So the same way the mapping class group is generated by Dane twists, The Torelli group is generated by separating twists and bounding pair maps. Powell was a student of Berman actually, and he left mathematics to enter a monastery. So there's a long story there. So I think Joan has described him to me as such a waste, of talent, but maybe I don't agree with that statement. So though he did prove a number of really spectacular theorems in his short mathematical career. Anyway, so this at least gives you a sense of how you might break down some elements of the Torelli group. And it shows you, for instance, that the Torelli group is typically a large group, right? So if someone first tells the definition, you think, well, maybe it's a trivial group. Maybe all there is the action of homology. And for some higher dimension, but in low dimensions, definitely the action of homology is just the first piece of information. Okay, so non-finiteness properties of Torelli. So this theorem right here, I said generated by separating twists and bounding pairs. I don't mean that it's finitely generated by them. Okay, because that's it's generated by all of them. There's a lot of separating curves on the surface. There's infinitely many. A typical separating curve will just go everywhere. Like there's so this is giving a generating set, but definitely not a finite generating set. So the Torelli group is an infinite index subgroup of the mapping class group, and so we expect any finiteness properties the mapping class group have do not necessarily descend into Torelli group. So an example, like a sort of more pedestrian example. If you take the free group F2 on the free group on two generators, that's like the most finitely generated group, right? It's very finitely generated. On the other hand, its commutator subgroup, as you learned when you first learned covering space theory, the commutator subgroup is an infinitely generated free group. So in the land of groups, unlike the land of vector spaces, passing its sub-objects typically makes things bigger rather than smaller. Okay. So if you have an infinite index subgroup of a group, even if the group itself has any finiteness property you might imagine, the subgroup has nothing. There's nothing you can say in that. Okay. And so if you're a pessimist, you should think, well, then the Torelli group will not have any, the mapping class group is great, but the Torelli group should be pretty terrible. And the first hint of that spoke about, I should say, like the first in genus 1, it turns out that the mapping class group is everything is given by the action of homology. So the genus 1 Torelli group is trivial. So the first non-trivial case is in genus 2. The same, and by the way, on a torus, can you draw any separating curves? Well, one's the bounded disk, right? Can you draw a bounding pair map where you have two curves that are actually homotopy? So there's no way to actually, that generating set statement I told you, it doesn't give you any interesting things on torus. You need a genus 2 surface to have room to write down any of these things. So the first non-trivial case is genus 2. And in fact, in theorem of Jeff Mass from 1992, says that the genus 2 Torelli group is an infinite rank free group. This is a, sort of dispiriting theorem. The proof, though, is amazing. The proof actually uses like the 100 years of geometry of the moduli space of curves. It uses subtle properties of moduli spaces of curves in a billion varieties. It does embedded Morse theory on spaces in a billion varieties. I mean, it really is. It's a purely topological theorem, but it's really but the proof is algebra geometric. There are now topological proofs due to Margaret Hatcher and Margaret. That's been a boost in Margaret. So, but basic proof is really remarkable. That's why I put an exclamation point with it, right? This is one of my favorite theorems. Not so much for the statement of the and this was generalized. So this statement I'm giving here combines work of Vespina, Books, and Margaret from 2010 with Guy Pullen from 2018 that said that for G at least 2, in fact, the D homology of Torelli with rational coefficients is infinite dimensional when D lies between 2G minus 3 and 3G minus 5. So you notice that for G is equal to 2, this says 2 is 4 minus 3. It's 1 is less than D is less than 3 times 2 is 6 by 1. So 1 is less than D is less than 1. So it says only something like H1 for genus 2, which makes sense. In the free group, that's trivial. Okay, so this is in fact a generalization of that part of Messi's theorem. The significance of the number of 3G minus 5. So Vespina, Books, and Margaret proved that was the cohomological dimension of the Torelli group. So in degrees above 3G minus 5, there is no non-trivial homology. Okay, so this says that near the cohomological dimension, sort of in some roughly the upper third of the cohomological range, the homology groups are infinite dimensional. We actually don't know how to calculate them. We can just write down we can write down infinitely many linearly independent elements, but we have like what they actually are seems kind of mysterious. I can't write generators for them or anything like that. So this theorem right here should suggest to you that, well, unlike the mapping class group, the Torelli group is pretty bad, right? It's pretty big, it's pretty infinite. But there are actually some surprising finiteness properties as well. So there's an amazing theorem of Johnson from 1983 that says that for G at least 3, the Torelli group is finitely generated. So Dan Johnson is another remarkable figure. He, the paper that I'm referring to here is, as far as I know, the only analyst paper that's ever been written by a homeless person. So he was, he was, he had a PhD, but in math, in outbreak ecology, actually, but he didn't really want jobs. He really loved the outdoors and stuff like that, so he lived in the woods most of his life, he would come in and work for a month or so of the year to get enough money so he could spend his time kayaking and mountain climbing and stuff. He actually got a full New York Times obituary, which barely mentioned his math. Like it mentioned his math at the very end because he also had a sort of early career in classical music, and so he invented minimalism. He was Lamont Young, who's usually attributed the founder of minimalism, attributed to his college roommate Dennis Johnson gave him the idea. So his music was rediscovered lately, like recorded in one of the words. And so, yeah, it's a remarkable New York Times obituary. Like it talks about all this stuff about music and about climbing, and then at the end it's like, oh yeah, he did some math. There's this thing called the Johnson homomorphism, which really people still study today. So, anyway. So this is this is G at least 3. So this is not true in genus 2, because remember, Mess proved it was an infinite rank free group. It's an open question. Is the Torelli group finally presented? Is H2 of the Torelli group finally generated? We just don't know. That's been a thorn in the side of people who care about these things since the 80s. It's really and for a long time, I always conjectured publicly that these were not true, that in fact it was not finally presented. But maybe you'll see why I'm going to change my tune, and maybe conjecture something else. Now, there is one potential finiteness property that's worth pointing out. So we have this short exact sequence. One goes to Torelli, goes to the mapping class group, goes to the symplectic group, and that gives us a spectral sequence converging to the homology of the mapping class group, right? We have HP of the symplectic group with coefficients and HQ of the Torelli group. That's the E2 page, right? That converges to the homology of the mapping class group. We have this thing right here that involves an infinitely generated homology of Torelli, right? Converging to something finite. And so there's a conjecture of decay that for all P and Q, in fact, all terms of the C2 page are actually finite dimensional, even though this right here is often infinite dimensional. So that's one like sort of weak finiteness property that's, I think, quite intriguing. By the way, so the fact that the Torelli group has infinitely generated homology, this calls back to Araki's right? We can't really know, we know things about the Euler characteristic of the symplectic group, and we know things about the Euler characteristic of the mapping class group, but they're not related because there's no way to define an Euler characteristic of the Torelli group because everything's infinite dimensional, right? So there's you can't say what infinity minus infinity. It's like you can't define an Euler characteristic. So, but Hayne does conjecture that. So that's one weak form of finiteness that you might guess. So now there's another form of finiteness. So implicit in here, of course, is that the I should say like this is no. So I told you that we know a lot about genus 2. In fact, we know all that so Mess didn't just prove that the genus 2 Torelli group is an infinite rank free group. He gave like basically a description of this first homology group. And using that description, you can prove that this holds in genus 2. And it also holds in a few other terms that we can work out. Like all the infinite dimensional homology groups that we actually know explicitly, that there are like some kind of like induced representation where you can sort of work out the homology with respect to the symplectic group. So implicit in there, of course, there's an action of the symplectic group of the homology of the Torelli group, and that is implicit in this short exact sequence. And that's what I want to explain next, because any sort of description you might give of the homology of the Torelli group should take into account that action. So what do I mean? Symplectic group action. So the mapping class group acts in a normal subgroup of the Torelli group by conjugation. Well, that gives us an action of the mapping class group on the homology of the Torelli group, right? By functoriality. But the Torelli group also acts on itself by conjugation, and that action on homology is trivial. That's just a general fact. If you have a group,
It always acts on itself by conjugation. The induced action on the homology of the group is trivial. Basically, what is the action of a group on itself by conjugation? That's sort of like changing a base point in the Eilenberg plane space, right? And homology doesn't really know. So we have the action of the Matherin-Cross group in the homology of the Torelli. That action is trivial on the Torelli group, so we get an induced action of the quotient mod G mod Torelli group. That's the symplectic group. We get an action of the symplectic group on each homology group of the Torelli group. This is the representation, by the way, that I promised you, right? I promised you I said there be linear representations of some group. And here they are, the action of the symplectic group, sp2gz. It's a group of matrices on the homology of the Torelli. Okay, and so any description you might give of the homology of the Torelli group should take into account this action, right? It should reflect all the symmetries that the Torelli group has. And so Johnson, in 1985, computed the first homology group for the Torelli group with rational coefficients. It has the following beautiful description. H1 of Torelli, Q coefficients, is like that wedge of H mod H. H is the first homology group of the surface. So the symplectic group acts in the first homology group of the surface. And so this is a description of it in terms of the representation theory of the symplectic group. This is an isomorphism of symplectic group representations. Now, we'll say, how does H live inside the wedge 3 of H? Well, yeah, you can use the symplectic form to give give one sort of canonical natural embedding of H into wedge 3 of H. Basically, there's a trivial representation inside a Q inside wedge 2 of H, that literally is the symplectic form. Then you take the third exterior column, it gives you a map of H into it. So we have that description right there. So this is quite a beautiful description. This is given by, I mentioned the word Johnson homomorphism. This isomorphism is given by what's called the Johnson homomorphism. So it is this very beautiful homomorphism on the Torelli group to wedge 3 of H mod H that somehow there's many descriptions of it. My favorite involves it sort of records cut products of mapping Torelli. So it's reporting sort of subtle second order topological information about the element of the Torelli group. So, but the feature that's relevant for what I want to talk about is that, so this is, I told you that the homology of the Torelli group is a representation of the symplectic group. Now, sp2gz, this looks a lot like a Lie group, right? Like sp2gr. You might be more familiar with the representations of Lie groups. So, or of algebraic groups. Now, there are many representations of sp2gz, but the nicest representations are the algebraic ones, those that are extend to the Lie group, right? So the Lie group or the algebraic group. So in this case, so sp2gq acts on the action of sp2gz on H extends to sp2gq, and so therefore this representation, which of H mod H, is actually not just a sort of random representation of sp2gz, but an algebraic one that extends to the algebraic group. Those are special. So there's many representations of the symplectic group that do not extend. So for instance, you can map sp2gz to sp2gz mod 7, right? Just by reducing matrix coefficients mod 7, and then take an irreducible representation of the finite group sp2g f7, right? So you get your representations that factor in finite groups, you have algebraic representations, you can get tensor products of those things. So there's sort of, the representation here of the symplectic group is quite the integral symplectic group is quite complicated, but the nicest representations of the algebraic ones. And this brings me to a folklore conjecture that in some stable range, something like this should also be true for the higher homology group. So for D at least 1, the deep homology of the Torelli group with Q coefficients is expected to be a fine-dimensional algebraic representation of the symplectic group once G is sufficiently large. So for instance, for H1, Johnson's theorem says it starts happening in genus 3. It's not true in genus 2 because H1 in genus 2 is an infinite dimensional representation of that. Starting in genus 3, it becomes not just a finite dimensional representation, but the nicest possible finite dimensional representation of the symplectic group. So this is a folklore conjecture. I think, yes?
Is this conjecture in some way related to the nice behavior of the stable homology of the moduli space? Or?
Yeah, let me tell you an open question about the homology of the Torelli group, right? So the stable homology of the moduli space is given by polynomials in these kappa classes, right? These Miller-Moretti classes. Now it's known that the even kappa classes come from the symplectic group. So they're pullbacks stable classes in the symplectic group. The odd ones do not. And so it's open whether those restrict the non-trivial classes in the homology of the Torelli group. A conjecture that I think Rita made was that in fact, if you look at the variant of these homology groups, that can be generated by the odd kappa classes.
the FP Gary part. So that's the relationship there. Anyway, so this is a folklore conjecture. I think I've heard about it back when I was a graduate student. It's been around for many years, and I never really believed it. I thought it sounded like I thought it was like, well, this is just optimism, and I don't, I'm not a very optimistic person. I believe that the world is, is a bad, scary place, and so like something like this should not be true. But now I think I believe it. So this is my theorem, as I want to talk about in the last little bit of time. H2 with the Torelli group. This is with Dan Minahan. H2 with the Torelli group with two coefficients. It's five-dimensional for G of x5, and an algebraic representation is selected for G of x6. So this is the first, the first actual progress in that conjecture since Johnson's work in the 80s. So let me make a few remarks about this theorem. So earlier, Minahan proved that H2 of Torelli was fine-dimensional for G of x51. So this was sort of a breakthrough. I proved, I sort of joined him on this partially, so I wanted to understand this theorem. I still actually don't understand his proof for G of x51. I tried very hard, but we have actually proven it's much stronger result. Now, assuming, so I told you that it's a sort of folklore conjecture that the homology of the Torelli group should be fine-dimensional and algebraic. So, assuming fine dimensionality, Coopers and Randall Williams actually calculated the algebraic part of the homology, at least of H2 of Torelli. And so therefore the above said, combine the above with Coopers and Randall Williams work, we actually have a complete calculation now of H2 of Torelli starting at genus 6. So I don't want to state it. It's it's not as nice as which of H1 is, but it's you can write it down. It's still, by the way, open whether this holds with integer coefficients. I just don't know. I don't even know if it holds like for FP coefficients for large numbers. So our theorem just somehow doesn't give that. So I want to say just a few sentences about the proof in the last little bit of my talk. So I just put the theorem at the top so we don't forget it. So here's an obvious proof strategy, at least for fine dimensionality. So, well, let's go to surfaces with boundaries. So we have inclusions. We have a Torelli in genus 1 with a boundary, and Torelli 2 with a boundary, Torelli 3 with a boundary. These surfaces embed in each other, right? A sort of increasing union of surfaces. And we can extend, take an element of the Torelli group in genus 2, we can extend by the identity to get an element of the Torelli group in genus 3, and so on. Okay, so we have this increasing union of groups. And it gives you a sort of sequence of maps of the Torelli, of the homology of the Torelli group. Oh, there's a typo. That should be not H3 of Torelli, H2 of Torelli. Okay. Anyway, so how might you think? You might try to prove this by induction, right? You might want to first prove that, say, H2 of Torelli 5 is fine-dimensional, using maybe some special features of homology in this case, and then prove to show that that persists in higher genera. You might prove, say, that the co-kernel of the map on H2 is fine-dimensional, right, for large enough genus. So that would say it starts being fine-dimensional in genus 5, and then at least, if the co-kernel of that map is fine-dimensional, that means it continues to be fine-dimensional in higher genera, right? So that's a sort of natural proof strategy. It's obvious. Many theorems about the Torelli group have been proved like this. Sort of my thesis, like, was entirely devoted to developing tools for doing that sort of thing. But the problem is that there's no way to prove the base case of the induction. So you can prove. So for instance, the calculation of H1 of Torelli, it starts in genus 2 where it's false. Where Johnson's theorem is false, but we know exactly, we know a lot about genus 2. Like, it's a very special genus, and so you can sort of show that while it's not wedge tree of H, it's close enough that you could somehow get the induction going using very special features of genus 2. But genus 5, I know special features in genus 2 and 3. I don't actually know any special features of the Torelli group in genus 4. And certainly genus 5 seems completely generic, so I wouldn't know how to do this. So there's no way to prove the base case of the induction. And so the solution, what we actually do is we show that we don't actually need a base case for this induction. Now that sounds kind of strange, right? So amazingly, it turns out that no base case is needed. And so here's a theorem. So for G at least 1, let VG be a representation of the symplectic group over a field of characteristic of 0. And let FG from VG to VG plus 1 be an SP2GZ equivariant map. Oh, I forgot, actually, it should be SP2GZ cross SP2. The SP2X trivially NVG. So there's a typo of the theorem statement right there. Anyway, so we have a sequence of representations with symplectic group and equivariant maps between them. And for G larger than some constant, assume that the co-kernel is fine-dimensional. So that, that's like the inductive step of the inductive proof. And something else, which I'll tell you in a second. The conclusion then is that BG is finite dimensional for G at least G 0+1 and algebraic for G at least G 0+2. Now, this is without some other condition, this is just it's obviously a false statement, right? So for instance, these could be like an infinite dimensional trivial representation of some lecture group in every genus, right? The maps could be data. So like this is not a true statement right here. You need something. But you actually need very little. It turns out that all you need is to rule out exactly that problem. You need to rule out infinite dimensional trivial representations. So you have to assume that, well, not the invariants, but the co-invariants, the SP2G co-invariants are finite dimensional for large vectors. Then this is true. I find this theorem very hard to emotionally accept, even though I proved it. And I should say, like the proof of finite dimensionality is not very hard. Proof of algebraicity is very hard. It's not a formal theorem. It uses ingredients include Margulis's work on superrigidity, Blavatsky's work on the algebraic whole of arithmetic groups. It uses an awful lot of facts about the representation of finite shape Lie groups. We use Whittaker models and stuff. We really use everything I know about that. And then we have to do a computer search to rule out characteristic two issues. So this is not a formal theorem. This theorem uses a lot of sort of subtle structure in the representation of these groups. But that's how it works. So we just apply it with H2 of the Torelli, H2 of the Torelli group. It turns out the co-invariant statement is very easy to prove. That was basically known already. And then the co-kernel statement we proved by studying the equivariant homology of the action of the Torelli group on spaces of curves with some fixed homology classes. That's all I want to say about that. So thank you. Yes.
So when you say that it's finite dimensional of G different and other and G different, does it mean that you have one particular value for which it's finite dimensional but not algebraic? Or that
We don't know. So we don't know if it's algebraic. In fact, so I told you we had to exclude these like really degenerate characteristic two issues. And so there's issues in characteristic 2 and 3 that we can't handle. But I suspect that this should be finite dimensional algebraic for all G of this G 0+1. But just so there's things about the representation of finite shape Lie groups in low genus and low small primes that are just they're too complicated to prove by computers. But they're probable, but they're just too complicated.
So like for the G equal to 5 that you had before, that do you know? You don't know it.
I have no idea. No idea. So, but I suspect it does. And because I suspect that like this theorem, if I can rule out these small characteristic issues and get it down to the optimal theorem, I can probably do that. Yes?
Do you think you can get a similar theorem to this or other?
Oh yeah, yeah. I think I can do it for like S something, I can do it for all of us. Questions? But if not, so I think I need.
For example,
Yeah, I mean, so that's right. Yeah, so I told you I don't need to know how to make it science. I can't improve the high dimensional but with other coefficients for consideration. Like that, like it probably is. I mean, probably it's kind of fine better or overseen, but